I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics. And in this video, we're going to be looking at physical chemistry for the life sciences, where we're going to be overviewing chapter 3 in this, which is phase equilibria, which is part of the Biochemical Thermodynamics Part 1 section of this textbook. And this book is a common book used in physical chemistry, taught for biochemistry at Arizona State University for physical chemistry with a biological focus. This video is meant to briefly overview the topics covered for phase equilibria in this book. And we're going to do this just by making a single slide and giving kind of an overview of what's happening in the textbook for each of the 10 different subsections in this chapter 3. So looking at these different things. And I would encourage you that this textbook is very readable, has a lot of great examples in it. And then, as I've always stated, the key concepts are covered at the end and summarized along with equations, and the way to really get a handle on this material is to really work problems. So the exercises and projects I consider critical here, along with some of the discussion questions, which basically go back and test some of these key concepts that you learn as you go. So now let's dive into phase equilibria. And the book starts by reminding us what we've looked at when we were looking at the laws of thermodynamics, which is conditions for stability. And I pulled this up from the previous chapter, chapter 2, when we were looking at the second law, showing that what we're often doing by the second law is finding, the maximum in entropy of a system. And this often corresponds to finding the minimum energy in a system. And when we're looking at chemical systems, it's often looking at the Gibbs energy, or often called the Gibbs free energy. And this is because we're often doing things at constant temperature and pressure, and we're looking at the equilibrium in some type of chemical or biochemical process, which means changing the number of moles in a system. And so it's kind of looking at this that we're going to, look at in a fair amount of detail. And so I even like to go back and kind of remind us of a few things. In fact, I probably start almost all thermodynamic processes back from what we covered in chapter 1 and 2, which is that we state that the change in internal energy is the change in heat and the change in work. And I'm adding these. You could also make it kind of a small delta to indicate that these are path dependent, while this is an exact differential, a state function that is path independent. Now, once we do the combined first-second law, now we know that if we're talking about reversible processes, equilibrium thermodynamics in reversible processes, that this is coming as temperature, the change in the entropy. And usually, for the first 2 chapters, we were considering kind of the most common, simple type of work, mechanical work in 3 dimensions, or basically PDV, or pressure volume work, with no other additional work terms. Now, in this chapter is really where we're going to get to one of the most important, in fact, what I would say is the most important type of work, chemical work, is what we're going to be looking at in this chapter and introducing. But for now, this is how we often look at this. And what we saw was when you change things, like for example, to the enthalpy, what that is the enthalpy is defined as U plus PV. And so now that's a Legendre transform on this. And so now we can look at this energy, instead of the internal energy, we can look at an energy that is called the enthalpy, and that is TdS plus VdP. So now we've changed our dependent variable from volume to pressure. And so under constant pressure conditions, the change in enthalpy is related to the change in heat. Well, what the Gibbs energy is a double Legendre transform. So it has this term in it. In other words, it has H and then minus Ts. So you can also write this as H minus Ts. And so and the way I remember this is that whichever of these, it takes it flips the variables and flips the sign. So it flips from minus SdT plus VdP. So now our dependent variables are temperature and pressure. So if those are held constant, then there's no change in Gibbs free energy. So what is progressing here? It's usually this extra work that we would have over here. So, the chemical work or the number of moles of something changing. And so the first part of this is taking what we've looked at as our formulation for looking at these various types of energy, starting with the laws that define it by the internal energy, and then switching to variables or other types of energy that are convenient for the variables being changed and or held fixed in specific experiments, chemistry and biochemically related experiments. And getting to the one that we often use most often, which is the free energy, because of the commonality of doing things at fixed temperature and pressure, and therefore letting us focus on any additional extra work terms, which are often chemical work terms. So now we're going to explore the Gibbs free energy in more detail. And so we said that this will come as minus SdT plus VdP plus, and now I'm going to write explicitly the sum on mu I dNi. In other words, the chemical work, the chemical potential of into the change in the number of moles for each ith component in a system, right? And so, this is often fundamentally where we're starting, in some of these. So specifically, when we're looking at a single component system, so this is starting by looking at phase equilibria. So one component, the most common is something like water, right? Where we're looking at it changing its phase. And we're familiar with, both in the fundamentals chapter here as well as from introductory, these are from the three phases of matter, from solid to liquid to gas, right? And so this is a good example of where you can get a good intuition for this. So if we're a fixed number of moles, we're not changing the amount of material, we're changing the phase of something. We're looking at it as a function of pressure. And what's implied here is that this is at constant temperature, right? So what is at, so if temperature is constant, number of moles is constant, then dG dP, how the Gibbs free energy changes with pressure at constant temperature and number of moles, is equal to the volume of the system. So which does, for a fixed number of moles, which one has a larger volume? A gas has a much larger volume. Liquids and solids can vary. Famously, solid ice can be less dense than liquid water. But the solids and liquids typically have similar densities or volumes, and the gas typically has a much, much higher. So that's what gives it a much, much larger slope compared to the solid and liquid. And we're always staying at the lowest free energy. So at low pressure, we have a gas here. Can change the color to be able to see. So we have a gas here. And then this is where this is the pressure at which the Gibbs free energy of the gas and the liquid are equal. So you will, if you keep trying to increase the pressure, you'll convert your gas into a liquid. And then the liquid will increase its pressure until you get to a point where the solid is the lower free energy state. And then this is where it will solidify or crystallize into the solid state, and then you'll start compressing it. Now it shows, so that kind of explains why these have positive slopes. These are positive volumes, or volume is a positive quantity. And why the gas has a much larger slope than the solid and liquid. Now this one is shown to have curvature, while these are not, and that's because if you look at the second derivative, so how the volume changes with pressure, right? The volume does change with pressure significantly for a gas. In other words, it's compressible, while the volume of solids and liquids to first approximation are considered incompressible, not compressible. And so that's why they're straight lines or don't have any curvature to them, which is the second order derivative of this. So this is hopefully giving you a sense of how using kind of calculus-based methods for developing thermodynamics really helps us to understand these graphical diagrams and understand at a fairly fundamental level of what's going on in these phase equilibria and phase transitions. And then we turn around and do the same thing, but as a function of temperature. So as we said, the Gibbs free energy, so I'm just going to write the first two terms, right? So we're looking at it, the Gibbs free energy is a function of temperature, pressure, number of moles. And so we've just looked at how it changes with pressure. Now let's look at temperature. And what is this assuming? This is now holding constant pressure. And this, you would say, we're probably more familiar with. Instead of varying the pressure, what we're typically used to doing, especially in phase equilibria, think of melting ice or even boiling water, et cetera, we're usually trying to vary the temperature while we hold things at a constant fixed external pressure of usually an atmosphere, right? So this will probably be much more familiar. So at constant pressure, meaning this term goes away, then the partial molar quantity we're interested in is how the Gibbs free energy changes with temperature at constant pressure and number of moles, right? Which we have it. And that goes as minus the entropy. Entropy is a positive quantity, so minus the entropy will mean that we have a negative slope. And the larger the entropy, the larger the negative slope. So the gas has the largest negative slope, and then the liquid, and then the solid has the most shallow negative slope associated with it. And again, we can follow which one has the lower molar free energy at low temperatures, being the solid, and then where the molar Gibbs free energy is the same during the equilibria of those phases, and then you can go and just heat up the liquid until you get to where the molar free energies of the liquid and gas are the same, boiling, and then you can heat up steam or heat up the vapor of whatever the material is. And so this is showing you the temperature of freezing and the temperature of boiling. And you can see where you stay along the lowest free energy path of all of these. So hopefully, and then again, we could look, why are these mainly straight lines? Because that would be the curvature of this, or how the second order derivative. So how the entropy changes with temperature, which is related to the heat capacity. And in general, over fairly limited temperature ranges, the heat capacity of most things, both solid, liquid, and gases, are typically fairly fixed unless you get to really extreme low temperatures, etc. So the first approximation, that's why these are drawn as straight lines. You can be more precise with these graphs and give them the correct curvatures by looking at these heat capacities specifically and looking at how this slope changes or how there is curvature in this. So the book goes on then to look at phase diagrams in general, reminding us of things we've already seen, you know, the stable fields for solid, liquid, vapor, what a critical point is, triple points, you know, where the phase equilibria is between solid, liquid, between liquid, gas, etc. It shows it to you in a much larger pressure regime where you can see almost all materials have multiple polymorphs, or if it was an element, you would say allotropes associated with it. And so oftentimes, you know, the solid field between different polymorphs or crystalline phases of the same material, the same compound or substance, you know, can occupy a large amount of phase space, right? And oftentimes we focus in on this one, especially in biology, but at very high pressures, you can often get a lot of different solid substances. And it focuses on kind of anomalous liquid-solid lines versus more typical ones. In other words, ones where the solid is less dense than the liquid, and ones where more commonly the solid is more dense than the liquid. And the reason for this, and it's very critical in when we're looking at life sciences, is because water is one of those anomalous materials. And it spends a fair amount of time discussing water phase equilibria. And then importantly, it quickly moves to going on to looking at biological materials, both things like the unfolding of proteins, and how that can look similar in its analogy to phase equilibria of simple kind of, you know, liquid solid type transitions or you know, melting type behavior, like in the denaturization of DNA to single-stranded, etc. And so often these are even kind of given the same terminology, like melting temperature, not indicating that this is really a crystalline solid melting to a liquid, but it has a lot of the same similar properties, so it often gets called this. And a lot of this really is learning a lot of the terminology that goes along with looking at phase equilibria, reminding you of basic phase equilibria that you've seen before, and then going on to give some of the terminology used in looking at phase equilibria for biological systems. So this carries on into lipids and membranes, where it will talk about these. And the reason we introduce some of those solid and liquid is because a lot of times biological systems have things like in these membranes where it's a liquid crystal type transition. And there's a whole field of phase equilibrium associated with liquid crystal phase transitions. And the book gives some very relevant information specifically for biological systems or lipid systems, where you can get these things that look like chain melting, is what they often call them. And they draw phase diagrams associated with denaturization of things like protein, where you use some type of denaturant to look at native proteins versus ones that are unfolded or random coil, and even some intermediate stages like these molten globules, etc. And you can draw things that are analogous to these phase equilibria between solid, liquid, gas type things in a single component. They have analogies to that in looking at biological systems. And so it goes through some of the main ones like nucleic acids, like proteins, like lipids to form membranes, etc. So then the latter part of the chapter really focuses in on chemical potential. And so it starts by reminding us that, as we said before, that this goes as minus SDT plus VDP. And like I said, this is where it really starts to introduce that the chemical work is the chemical potential into the change in the number of moles in a system for each of the components. And really what this is driving to is looking at multi-component systems now, where what we're going to be doing is often doing things at constant temperature and pressure so that the Gibbs free energy is just the chemical work in the system. This is the only work term allowed to vary, and it's often called extra work, etc. And specifically where we're looking at the partial molar quantity of this, holding all other components fixed, so holding temperature and pressure fixed, obviously, but also, any other component that is not, that is not the ith component. So all other components except the ith component held fixed, and this will be equal to the chemical potential of the component, the partial molar quantity. And so this is often just given this for the molar quantity, and then whatever the ith component is. And your book this book, as well as most, would start by just calling it the eighth component, and then the B component, C component, etc. of this. And so it's really giving you an introduction that the partial molar Gibbs free energy is the chemical potential. And that's going to be a critical point moving forward, that each of the individual partial molar free energies is related to the chemical potential of that component. So, and it's introducing this idea of partial molar quantities in general. So the Gibbs free energy is what we're mainly looking at here, but you can look at a lot of different partial molar quantities when you have multiple components. And this is a very common way and useful way to look at this. So then the book, and this is a very, in a sense, long subsection. And so I've just shown one component, but it starts by actually showing the chemical potential as a function of pressure in these systems. And that's very common because you're going to look at the Gibbs free energy at constant temperature when you just have a volume pressure. And this is often how this is developed in kind of an ideal gas way to show, some of the setup for chemical potential. I've gone on to show here something that after it kind of introduces it from reminding us of kind of ideal gas behavior and what some of the chemical potentials look like as you start changing the number of moles of gas and having gas mixtures, etc., on to looking at mole fractions of typically liquid solutions here. And it really gets to, towards the end of this section, looking at both these ideal dilute limits as well as the ideal solution itself, or Henry and Raoult's law behavior, from moving from where you have pure solvents to where you have an ideal solute that's very dilute in solution, to where that dilute solute gets to be a higher and higher mole fraction where now it's the solvent, right? As you go above a mole fraction of 50%, it's the majority component. And so this is really critical in looking at biological systems. And the book goes on to describe quite a few different biological cases for looking at mixtures in these materials. So, and then finally, the book gets to colligative properties, which again have been introduced in introductory chemistry, and specifically looking at them for biological systems. And so it first reminds us of kind of some of the freezing point depression, boiling point elevation, but puts it, because now we've more rigorously looked at the chemical potential and how the chemical potential of solutions lowers with respect to the chemical potential of a pure substance, which is usually done with an asterisk. And that lowering will then change, will cause a freezing point depression or a boiling point elevation. And again, we can look at this, it's how the chemical potential changes with temperature is how the Gibbs free energy changes with temperature. So again, these goes as entropies, etc. So relating back to what we saw in chapter 2, and a very good job of kind of putting graphical diagrams to some of this. Now, while this is relevant, really one of the key aspects here is to get on to osmosis and its real relevance in biological systems. So not only how to kind of measure osmotic pressure, but critically getting on to a seminal part of biochemistry where you can use osmotic pressure, which is critical in living cells, that they can develop osmotic pressure between inside and outside of cells, and it can be used in many useful measurements. For example, you can determine the molar mass or molecular weight of something like a protein by looking at how its osmotic pressure changes with the concentration of that protein. And it kind of mirrors ideal behavior as discussed. And so the book gives quite a few examples of osmotic pressure, not only several different ways of measuring it, but usefulness in life sciences and biological systems. And then, as I mentioned, this kind of overviews the chapter, which is quite long, has quite a few figures, goes through a lot of different examples, and then so there's a lot of exercises and projects that will really help you by working these, understand all the concepts that we've overviewed here and overviewed in the book chapter. Because I've just provided one slide on each one, you can probably see there's actually a lot of figures and a lot of information in this chapter that I've skimmed over, but that there's a lot of examples given in the textbook. And then, of course, at the end, it gives kind of some of the key equations and gives a lot of good discussion questions. So hopefully this helps kind of overview this critically important chapter as we move on to understanding biochemical thermodynamics. And this is getting us in from phase equilibria onto chemical equilibria next, and we'll continue in this series. Thank you.